Okay, so today we're going to be covering the equilibrium constant Kc. Now, Kc was taken out of the spec last year for the Wjec A-level chemistry and AS, but this year it's back in. So if you sat the exam in 2022, you may not be too familiar with the Kc. So this is a standard equation for Kc. So Kc is products over reactants, is another way to remember it, and it's all working out how far the equilibrium has gone in terms of making a product. So with this, we can use maybe a standard equation to solve this. So the standard equation would be H2 plus I2 gives 2 lots of HI. Now, this is a standard one because, for one, it doesn't contain any units when we do Kc, because remember, with units, to work out, you have to work out like so. So it's products over reactants. So in this case, it's going to be mole per decimeter cubed squared because of this stoichiometry here. And on the bottom, it's the same. It's moles per decimeter cubed, and it's 2 of them, so it's still moles per decimeter cubed squared. And these just cancel, so there's no units. So Kc is showing that we have a lot more product than we do reactants, or vice versa. So if you're high Kc, you've got a lot of product. High Kc equals a lot of product. A low Kc, this means not a lot of product. Now, if that's something you don't really want to learn, you can kind of visualize it in this way. So if you think about it, if you've got a high concentration of, let's say, product, that must mean you have a low concentration of reactant. So remember, anything, so if you do 1 over 0.01, that's going to give you 100. But if you do it the other way around, you're still going to have 0.01, but it's going to be a lot smaller than 100. So, in terms of the basics, that's fundamental. Now we need to move on to more of the A-level stuff. So the A-level stuff would be that the only factor to affect Kc is temperature. Now, if you think about it, we said there were a few things that changed the position of the equilibrium last year, and we did that in terms of Lucius-Hellier's principle. So we said that if you have more concentration on maybe the reactant side, the system's going to move to negate that change, so it's going to go towards the products. But in reality, because it's in equilibrium, in dynamic equilibrium, eventually it's just going to equilibrate back, and you're still going to have the same ratios you had before. Now, what you kind of have to recognize is that because temperature, if let's say this is an endothermic reaction, let's say it's plus 63 kilojoules per mole, increasing the temperature is going to push it further to the right. And there's no question about that. There's not really much change in which it can do to negate that. I mean, it can negate it, of course, by going the opposite direction. So if that was minus 63 kilojoules per mole, then yes, it would go that way, but it would still change Kc. So let's say all of these were gases. We said last year that an increase in pressure is going to move it towards the side with the lesser amount of moles. Now in this case there won't be any change because they are both equal sides, but let's say we had 3 moles on that side. It won't balance, but hey, so by that logic, if we increase the pressure, we force it to go more towards the product side, but eventually equilibrium will just take place. So even if we push it that way that much, over time, yes, we may only have that much of a push at the start, but eventually after a certain amount of time, it's going to equilibrate. So now concentration is the same if I had a load of H2 into this and had a lot of this. At the start, yes, you would get a different value of Kc because yes, it would push it towards this direction. But after a certain amount of time, it's going to equilibrate and it's going to start going back this direction too. Now, catalyst is one thing we always said didn't change Kc, and it still doesn't. Nothing's changed. So in terms of Kc, there isn't a lot more. I'm going to be going on to Kp in my next short video.